Assalamu alaikum and very good morning, dear students. Today we are going to start with an important course, lecture on important course, engineering mechanics. In order to illustrate the significance of engineering mechanics, I will start with a small story. In ancient Tamil Nadu, there was a village. In the village there were two celebrities. One was a boxer, who was the champion among the boxers of the surrounding villages, and another one was an intelligent man, a scholar, say a saint. One day, the boxer went to see the intelligent man. Champion among the boxers in the surrounding villages, and there was another intelligent man, scholar, say saint. So the two were the celebrities in the village. The boxer, he has got so much muscle power, nobody is there to talk a word against him. Okay. Intelligent man, he used to solve many problems. What are all the problems the villagers face, he used to solve the problems. One day, the boxer went to meet the saint, and he said, "Sir, we are two celebrities in the village. Suppose if you join hands, we will become the superpower in the village. We can rule the village as we like. Why don't we come into an agreement?" The intelligent man, the saint, asked, "So you are equal to me? Do you think you are equal to me?" "Yes, I am. I am a boxer. I have a good muscle power. I can do any hard work. Nobody can dare to fight with me." Then he said, "Okay, if you are so powerful, let me test you." Okay. He has taken out a silk kerchief, a small silk kerchief, and gave it to the boxer. How far can you throw this silk kerchief?" He said, "Oh, I have thrown many weights, many discs, hundreds of meters. This is very, very small kerchief. I can throw it far away." He said like that and tried to throw the kerchief. Can it be thrown? No. He tried to throw it, but it fell down in a very near distance, in a closer distance. He tried many times, but could not. The intelligent man laughed at him, and he took the kerchief and he put one small stone in it. Then he has thrown it. He has went very far distance. He said, "You said you are so powerful. You can do many, many hard works, but you cannot even throw this very light kerchief." Like that he said. Okay. So from this we can understand why I said this example. People are competing on powers. Okay. Everybody wants to be more powerful. But the real power can be obtained if you do some work. Power is the capacity to do work. We define the power as capacity to do work. So what is work? Work is manipulation of forces. You have to work against some forces, you have to work with some forces. That is why we call work is done. Work is done on it, work is done by it. So the work refers to manipulation of forces. So we need to study the forces acting on any body, any object, any particle in order to have the power. So the study of forces, a study of effect of forces on the bodies or particles is one. Everybody needs power. Power is the capacity to do work. Work can be done with the manipulation of forces. Hence, the study of effect of forces on the body is necessary, is widely known as engineering mechanics. For example, if you are an automobile engineer, you may need to know the various forces acting on every components of the automobile to design the vehicle. So you may have forces acting in or around the automobile. You may have wind force, you may have forces on the components, you may have forces on the connecting rod, you may have forces developed inside the engine. So all these forces you have to manipulate in order to design the power of your vehicle. Similarly, if you are a civil engineer, you have to consider the forces acting on beams and columns to design a structure or to build a structure. Similarly, if you are an electrical engineer, you have to consider the power of the motor. If you know the torque of the motor, you can find out the power of the motor. So in order to determine the power of the motor, the torque is to be known, or the force. Torque is a generalized form of force. An aerospace engineer or an aeroplane may need to consider the various forces acting in and around the aircraft to design and analyze the aircraft. So that is why we say that engineering mechanics is the effect of forces acting on the body or particles. The forces may be known forces or unknown forces or static forces or dynamic forces. Okay. But these forces maybe we have to consider in order to design a system. Either it may be a mechanical system or it may be an electrical system. So engineering mechanics is not just related to mechanical engineering, it has got a multidisciplinary application. Even if you are an electrical engineer, you may have to know the concepts of mechanical engineering, concepts of engineering mechanics. Similarly, if you are a computer science engineer, if you are dealing with the hardware, for example, you have a disk drive. The disk drive, it opens and closes, it has got a mechanical component in it. So you should know the power of the motor which opens or closes the disk. In order to know the power of the motor, you should know the torque, again the forces are to be studied. So similarly, if you are in the robotics, okay, you have to study the different movements of the robot. The robot is to be moved around in order to complete its task without any jerks. So it again demands the study of forces. Okay. So that is why engineering mechanics is necessary for every engineer, irrespective of the branch. That is why in our curriculum we have included engineering mechanics for many of the branches. And in general, in order to study a system or a body is generally made up of discrete components. Okay? Discrete components like atoms and electrons. Each particle may be made up of atoms and electrons. Engineering problem cannot be solved if we consider the particle as such made up of atoms and electrons in a discrete manner. Okay. So we have to consider it as a continuum. For example, if you consider a plate, a metal plate, in reality, the idealized system, it is a solid plate. But if you look at the micro level, the microstructure of your metal may consist of many atoms. So atoms, they are joined by bonds, they may have voids. Okay. So if you think that there are voids, you will not be able to analyze the metal plate. So we assume that it's a solid, it's a continuum. That is why we call this a continuum hypothesis. Okay, we apply engineering mechanics by considering all the bodies as continuum, and that is why this is called as continuum hypothesis. And regarding the mechanics, it's classified into three major branches: rigid body mechanics, which is dealing with rigid bodies, the bodies which do not change their shape, or there is a negligible change in this shape by the application of force. They are called as rigid bodies. And the next one is deformable bodies, which do change by the application of force. Bodies which undergo changes. If you consider 2 points of the body, the distance between the 2 bodies changes when you apply the force. So these bodies are called deformable bodies. Similarly, we know fluids. So what is a fluid? Mixture of gas and liquid. Which one is correct? Is it a gas or liquid or both? The one which can flow is called fluid. The one which can flow. Gases, they flow. Okay. Similarly, liquid, if you say, they also flow. So it's study of gases and liquids. Okay. So these three branches we apply. Okay. Generally in our curriculum in engineering mechanics, what we are going to study, we will be dealing with rigid body mechanics. Okay, rigid body mechanics. Again, the rigid body mechanics can be classified into statics and dynamics. So study of bodies in equilibrium is called statics. Okay, it is about the bodies at rest or in uniform motion. Equilibrium may be, okay, we will say equilibrium, there are again two kinds of equilibrium, static equilibrium and dynamic equilibrium. Okay, so if a body is in equilibrium, so that is called, we will be studying the bodies at the equilibrium, that is the statics. And in dynamics is concerned with, geometrical aspects of the motion, or it may be forces which causes the motion. Okay, it may be again two branches, but in general, study of bodies which is in motion, study of forces acting on the bodies which is in motion is called dynamics. Okay, so there are two branches. So our curriculum is designed in such a way, we will be studying about statics as well as dynamics in our engineering mechanics. So that is what I told, rigid body dynamics, deformable body mechanics and fluid body mechanics. And in the particle size, another classification is according to the size of the particle. The size of the particle is larger than the atom, or the velocity is smaller than or less than that of light, we call this as classical mechanics. Generally, what we are studying is under classical mechanics. Suppose if the particle is reaching the size of the atom, or its velocity is reaching the velocity of light or speed of light, then that will be called as quantum mechanics. It's beyond the scope of the subject. We will be dealing with classical mechanics. Okay? This already explained. Now we will come to the history. If you say, as I told in the introduction class, engineering mechanics, the word mecha refers to lifting of weights. Okay, the concept of mechanics were used in ancient history for building giant structures. If you see, they have constructed big pyramid. Okay, very giant pyramid. So how they would have handled the weights of blocks, stones, etc. Okay, so the major task they were facing during the building of such giant structures would be lifting of weights. So many theories were developed in order to lift the weights. That is why the mecha in our mechanics is the Greek word which means lifting of weights. Lifting of weights. In the ancient history, if you see, even in the 200 BC and 280 or 211 BC, they were using the concepts of mechanics in order to lift the weights. So the Archimedes, the book of Archimedes, it's famously known as book of Archimedes. It was dealing with some concepts of mechanics. Okay, so it was discussing about the principle of lever. So what is the first machine the man has developed, man has invented? It is the lever mechanism. Okay, crowbar and lever is the first machine. So the principle of lever, lever is used to lift the weights or manipulate the weights, move the weights. Okay, so the lever mechanism, the principle of lever was discussed in the first paper of Archimedes in the 287 BC itself. Okay, so after that we have to wait for the real engineering mechanics concepts, but we use nowadays for the period of Galileo in the 16th century. He has developed some pendulum experiments. Dynamics part was developed. Then Isaac Newton, he has developed the laws of motion. Then there were Eulers, Lagranges, D'Alemberts. There were many scientists after that in the 19th century, 18th century. Okay. So the earlier engineering mechanics concepts were developed during 200 BC. 200 BC. Okay. After that, in the 15th or 16th century only, we have the real concepts which we are using. Even now we are using. Okay. So the concepts of Newton, concepts of Galileo were applicable for the particles which are larger than atoms. Okay. So the suppose if the size of the particle is very small in the size of atom, approaching the size of atom at the velocity of speed, the classical mechanics developed by Newton, the Galileo cannot be applied. We have to go for new concepts. Okay, so this is about the history. Now we will see some of the basics which we are going to use in our engineering mechanics. There are three quantities. Okay, basic quantities: length, mass, and time. We already would have studied in our school level. The length describes the size of a physical system. Mass is the one which can compare the activity of one particle with the other. It can be compared with mass. The time is a measure of successive events. And force is is a dependent variable. We say force is pushed or pulled exerted by the bodies on one another, either directly or indirectly. It has got magnitude, direction, and sense. And some of the basic laws we will see today. The Newtonian laws. The first law of motion: a particle remains in the state of rest or uniform motion if the resultant force is zero. See, the laws of motion are the Newtonian laws. Newtonian laws can be explained as per our requirement. Okay, suppose you want to balance some system, it can be explained with respect to balancing. And if you want to consider the motion, it can be explained with respect to motion. Here, as engineering mechanics is dealing with the forces, we explain them, we define them with respect to the force. So if the resultant force is zero, a particle will remain in the state of rest or uniform motion. If the resultant force is not zero, the particle will be having an acceleration which is proportional to the magnitude of the force, and it will accelerate in the direction of the application of force. Okay. So this is the second law. And the force of action and reaction between the bodies in contact will have same magnitude, same line of action, and opposite sense, that is defined by third law of motion of our Newton. Okay. Newton also, the Newton first, in the apple principle, So the law of gravitation was first developed by Newton. So the two particles of mass capital M and small m, if they are mutually attracted by equal and opposite forces, say F and minus F, then the magnitude of force is given by F equals to G times mm by r square. Okay. So using this, we can find out the weight of the object, weight of a particle which is above the curve. Okay. So the G refers to the constant of gravitation, and is equal to 9.8 meters per second square, or we say universal constant, gravitational constant or universal constant. And some tips regarding the units. Generally we use SI units in our curriculum. Okay. The international system of units. SI unit, the expansion of SI units is the international system of units. Okay. Actually this is abbreviated as SI by using the French word Système International d'Units. That is why we call it as SI units. Instead of IS units, we call it as SI units according to the French word. Okay. And generally we denote the units in lower case letters. For example, if it is kilogram, we denote it as kg. Okay. Meters, we denote it by m. Seconds, the time. In seconds will be denoted by S. All are small letters, lower case letters. Okay, kg, small m, small s. Okay, but there are exceptions. Suppose if they are called after individual scientists. For example, Newton. The force is given as Newton. One unit of force is equal to 1 kg meter per second square. Okay, so because according to the second law of motion, force is proportional to acceleration. The proportionality is given by the mass. F equals to ma. F equals to ma. Okay. So the m is mass in kg and acceleration is meter per second square. So 1 Newton of force is equal to 1 kg per meter per second square. Okay. Similarly, pascals. What is that Pascal? Where we use it? Where this unit is used? In fluids or in pressure. Pressures are generally denoted in Newton per meter square or Newton per millimeter square. So 1 Pascal equals to 1 Newton per meter square. So Pascal is named after the scientist Pascal. Okay. Also the other exception is the powers of the unit. Say if it is giganewton, we use G, capital G, or meganewton, we use capital M. Okay. And suppose if it is milli or micro, we denote it as M. We use M for milli and mu for micro. So these are the common tips for the units. And all this we know. Length is given in meters, mass in kg, and time in seconds, force in Newton. Force is derived from the Newton's second law, F equals to ma. It is defined as force which gives 1 meter per second square of acceleration to the mass of 1 kg if we are given 1 Newton of force, and is equal to 1 kg per meter square. Weight of the body is also a force. Okay. So the weight is defined as force of gravity exerted on the body and is given by W equals to mg, where m is the mass and g is acceleration due to gravity. If you go to the previous slide, to the law of gravitation, Newton's law of gravitation. Here, F equals to G mm by r square, isn't it? So F is the force, so we replace F with W, and that G capital M by r square, okay, that by your gravitational constant G, small g. Okay, so we W equals to, it becomes W equals to mg. So W refers to the force which we always represent in Newton, denote in Newton. Okay, W is the weight of body, which is weight, the gravity, it is the activity of one body over the earth. Earth is a particle which moves. Okay, we have another particle or another body which stands above the earth or on the surface of the earth. The force exerted between these two is given by W. Force exerted between the two, the mass of the body which we are considering. So these two is called weight. Okay, so weight is given by weight equals to mg. So this is about the units. Now, as we told earlier, when I was defining the force has got magnitude, direction and sense. That is why we call force as a vector. Since we are dealing with forces in our engineering mechanics, we have to know about the vectors. Some basic concepts of vectors are to be known. So the physical quantities are generally expressed as scalars and vectors. We know scalar quantity has got magnitude only. Okay. It is described by a positive or negative number. For example, mass, volume, length, they are scalar quantity. They have only magnitude. There is no direction for mass, there is no sense also. Okay. Whereas vector quantity has got magnitude, direction as well as sense. Okay. So for example, force is a vector quantity. It has got a magnitude. So much amount of Newton force we apply, and it is applied in a particular direction, particular angle. And what sense? Whether it is upward or downward or clockwise or anti-clockwise, left or right. So this is referred to as sense of the force. Okay. So magnitude, direction and sense. So that is why we call it as vector. So force, velocity and all are vector. Yes. So vectors are denoted by, suppose if you want to, vectors are denoted by an alphabet superscribed by an arrow. Okay, for example, vector A is given as A arrow. Okay, similarly, vector A has got a magnitude which is given by, so this is a positive scalar. Graphically, the vector A is represented by an arrow. If you want to represent the vector A graphically, vector A is represented as an arrow. Length of the arrow gives you the magnitude of the vector. Say for example, if you say this is A is a force, click once. So this is the length of the arrow. Length of the arrow is equivalent to the magnitude of our vector. The direction is given by theta, the angle. Okay, direction. And sense is given by the arrowhead, position of the arrowhead. Here the vector is facing upwards. Okay, so this is called sense. Sense is also important. Why it is important, we will see in the next slide. Yeah. Suppose if you multiply the vector by a scalar, for example, this is vector A, if you multiply by minus 1, so the sense has got changed. Instead of facing upwards, the same magnitude, same value, same magnitude, but the sense has got changed. Same magnitude, same direction, but the sense is changed. Instead of facing upwards, the vector is now facing downwards. The sense has got changed. Suppose if you multiply the vector A by 2, it has got same direction, but the magnitude and that same direction and sense, and the magnitude is changed now. Similarly, 0.5 A vector A. So, and if you now we will see about vector addition. So vectors of same type may be added to form a resultant vector. For example, if you consider vectors A and B, they are added to produce a resultant R. Okay. So the magnitude of the resultant vector is obtained graphically by using parallelogram law. Okay, the vector addition. So if A and B are the two vectors to be added to produce a resultant R, first this is the vector A, this is vector B. So these two are to be added to produce a resultant. Okay. So draw vectors A and B so that their tails are touching each other. Vector A is drawn. Vector B, we have to draw like this, their tails are touching each other. Then draw lines parallel to vector A from the head of B. Similarly, draw a line parallel to vector B from the head of A. So the two parallel lines will meet at one point, or this is the point connecting this intersection point and the beginning point will be the diagonal of your parallelogram. The diagonal of the parallelogram will give you the resultant vector R. So graphically, we can find out the value of the resultant vector. The resultant vector of vectors A and B if they are added. Adding two vectors A and B, the resultant vector can be obtained graphically by using parallelogram law. Similarly, there is another method which is known as triangular law. We can obtain the resultant of two vectors when added. So if A and B are the two vectors to be added to produce the resultant, then to draw vectors A and B are the adjacent sides of the triangle like this. We draw in the same order. That means we have to draw from A, starting point of A is here, the arrow head faces upwards. From the head of A, the tail of B begins, and so it should be continuous. Okay, it should be in the same order and adjacent side. It should be adjacent to A. A and B has to be adjacent. Then the closing side of our triangle will be the resultant vector R. Closing side of it. So this is called triangular law. We can apply either parallelogram law or triangular law in order to find the resultant of the two vectors. Suppose if you consider subtraction of two vectors, we have vectors A and B. We have to find the resultant difference between the vectors A and B. This is vector A. This is minus B. Okay. So if they are to be like this, then the resultant can be found by using either parallelogram law or triangular law. Say here you can look, vector A is in the same direction, this is minus B. So what happens? The sense changes. From the tail of A, we have to draw vector B in the opposite direction, the opposite sense. Okay. The angle remains same, whereas the sense is changed. Okay. Now you draw the parallelogram, the diagonal of the parallelogram will give you the resultant vector R. So you can apply this for triangle by using triangular laws. You can obtain this by using triangular laws. Okay? Okay? Any queries? Do you have any doubt? Go to the slide. Other people. Yes. Okay. So any queries so far about the vector addition, the previous laws of engineering mechanics? Any doubt? Yeah.
All these are
Yeah. It's the value of small g only. Gm m by r square. That is the point. I mean 9.8. Not capitals.
So in the census registration.
Okay.
So for the
You have to
so
just close it. It's a graphical method. Okay. There is an analytical method also by using cosine formula. You can find by using cosine formula the analytical solution. Okay. That is also there. We will see about it in next class. Now I will give you. We'll solve one small problem. Okay. How we are going to solve it? It's by using parallelogram. Okay. So for example. Now we will consider a hook. We have a hook of some machine member. It is pulled by two cables. We have one cable at this position and another cable goes like this. So we have to find out the resultant produced by the cables are pulled. So pull means it's a force. Okay. So some force, say 150 Newton, is acting. Okay. In this direction, pull. Then here, say 100 Newton is acting. Okay. So we need to find out the resultant force acting on this hook. Okay. Suppose if you have to design the hook. Okay. The net force acting on the hook will play a role. The force will produce a stress. If you are a design engineer, you have to see that the stress developed. Okay. What is stress? Intensity of force. Stress is nothing but how much intensely the force is applied. Okay. The intensity of force is given by, what is the formula for stress? Sigma is the denotation for stress. F over A. Force by area. Okay. Suppose if it is a circular rod of diameter D, then area we know, the force, resultant force, if we can find out the stress developed, and if this stress is less than your material safe stress. Every material will have a safe stress. Say for example, if you are using a steel, okay, mild steel hook, the steel will have around 300 megapascal as its safe stress. Okay, so 300 Newton per millimeter square as megapascal, the safe stress. So if the force is found and if the stress is found, the stress is less than our safe stress, then we can say the hook will not get affected. Okay, if the stress is more than the safe stress of the material, then we will say the force system is to be changed, or okay, some modification is to be done, so the stress developed will be less. So how to find the resultant of this force? Say for example, these two forces are acting with respect to some datum. We have to consider a reference system. Okay, we can use a Cartesian coordinate system. Say this force is at 10 degrees inclination from the y-axis, and this is of 15 degrees inclination to the x-axis. We can find out graphically. First, we will see about the analytical method in the next class. Okay. So we are supposed to apply parallelogram law. So we draw the coordinate system. Y, x. This is your force 150 Newton. How will you draw this line? You can adopt some scale. Say for example, 150 Newton equals to 7.5 centimeter. Okay, 2 Newton equals to 1 centimeter. Some scale you add and you draw this line 10 degrees to the vertical. 10 degrees to the vertical. So this line represents your vector. So vector has got direction, magnitude as well as sense. So this line we have drawn, say 7.5 centimeters, because we have adapted the scale of, okay, so 2 Newton equals to 1 centimeter. 1:2 scale. Okay, we have drawn it. Then similarly, we have to draw another line which is 15 degrees inclined from x-axis for 5 centimeters. So this represents 100 Newton. 100 Newton. So we have drawn the vectors, force vectors. Graphically, we have represented the force vectors. Now we have to complete the parallelogram. We draw a line parallel to the first force. Say this is F1, this is F2. Parallel to F1 from the head of your F2. Head of F2. Okay. Similarly, draw another line parallel to F2 from the head of F1. So these two parallels intersect one point, and if you connect this with our origin, so this will become the resultant vector. This is the diagonal of the parallelogram. This will become the resultant vector. So if you measure it and convert it to the scale, we can get the magnitude, we can get the angle, direction, as well as we got the sense. So the resultant vector can be completely formed by using this graphical approach. Okay, we represent vectors as lines in graphically according to the sense and direction. We obtain the parallelogram. From the parallelogram, we got the result. Okay.